give some. All right, this is a third time of our regular seminar. So as we understand the spirit of this seminar, so each of the participants are consist of the graduate students, either master level or PhD level, doesn't that much matter. So what we'd like to do from this seminar is to share some of the computation with the depth of the real, and I want you to proceed the computations from elementary linear algebra and also calculus. And once you finish your own computation, you can share your own inspiration and your thought. And eventually this would be used for the ingredients to make some conjectures from your side. And then as long as you are able to prove something interesting, that would be considered as your like the paper later on. But in terms of the seminar, because each of the topics are quite like the diverse and distinct, so I'd like to specify how do we listen each of presenters like the talk. So first, all calculations are related to the specific two-dimensional surfaces, including, of course, R2. R2 is our like the space that we mostly feel comfortable with it. R2, torus, two-dimensional sphere, or in some contexts, we'd like to identify it as so-called a CP1 or projective line of dimension 1 in the context of algebraic geometry and number theory, and hyperbolic space. So real two-dimensional hyperbolic space. So what I'd like to each of you to think of for the presenters, so not just today, but also the potential presenters for this seminar is, so I just want to just give you some like the focus on specific like the spaces. For example, so for U, it is important to establish the Monge-Ampere equation in the setting of the two-dimensional sphere, which is CP1, and the torus or the complex torus of dimension 1. So so if, for example, if you like take the presentation regarding the hyperbolic space, for example, then do not just take that computation in a setting of the hyperbolic space. Try to translate that language in terms of either the S2 or the like a torus in a way that what if the setting is now changing? Then how this like the computation works? Because we are not talking about the either the sufficiency and or necessary that we need to set up as a hyperbolic space, for example. So that's what I want you to think of so that you can directly ask. So of course, presenter might not have a concrete answer, but that's completely fine. So what if we change this setting from, for example, hyperbolic space to either the S2 or the torus? So what's the like the obstruction, or can we extend in any ways? I'm not asking you to study all like the known like the literatures to give that an answer. So I just expect your answer is based on your own computation. Doesn't matter that it could be right or like the wrong. It doesn't matter. So that you get develop your sense of the computation, what you did, and try to think about those like the abstraction with a certain like the reasonable classes. That's for U. For hedging, because hedging is working on the apply like the context of the differential privacy, and the normal distributions matters a lot. So the structure of the normal distribution is related to the hyperbolic space, whatever that is. So the hyperbolic space is what Andy is now focusing on to like share over complex numbers, so that you just need to think of. So now I have a one like the collection of one-dimensional normal distributions that I know how to handle for the computation of the Gaussian integrations and so on and so on. How those are related. So that's also the spirit hedging can think of and you can keep in your mind. So how these computations are related. And even the setting is now changing from, for example, as to the torus in the different like the context, you still need to try to translate in terms of the structure of the normal distributions. That's what I want you to try. And for takes part, so it is important to first like study the or stochastic computation over Euclidean spaces. But for those like the elementary spaces, our computation can be still explicit. So once you finish these computations, then you can also try to share. What if we try to extend this like the computation from the Euclidean setting to the all other like the spaces that we have mentioned? Then what's the like the obstructions and so on. So that's also the spirit, and try to make every description as explicit as possible rather than the general like the framework, the Osner frame bundle. But you can also introduce for that later on, but it's completely up to you. And also the part of the lambda, so it is just related to the either the CP1, P1, or the torus or the elliptic curve. So it is important to reduce the algebraic like the phenomena in terms of the Cauchy integral formula. So this is the basic like the spirit. So that, for example, if we already established the concept of the degree of the morphism from the projective variety to itself, for example, then the concept of degree is completely well defined in terms of the purely algebraic like the descriptions. That's fine. But I want you to like reduce that like the abstraction into the world of the complex analysis so that we can exactly see how the integration play a role either over like a C1 or just the hyperbolic like the truncary like the ball and so on. So and for the part of the Andy, you also need to think of once we establish the Riemannian geometric computation of the hyperbolic space by using complex analysis, then we also need to develop the language of the Riemannian geometry here. And then once you learn those like the Riemannian geometry languages such as the Lebesgue connection, Riemannian metric, Riemann curvature tensor, exponential map, geodesic, sectional curvature, Lich curvature, Jacobi field, geodesic variation, and so on and so on. Once you establish those languages, so for upcoming like the presentations also as well, you need to also reduce to the example of the hyperbolic space. So in the case of this like the simple setting, then can we explicitly describe everything? And today's like the presentation, in my understanding, is also in that spirit, so that we can describe the geodesics explicit accordingly. So that's what we are doing from this seminar. So I don't really care again that whether or not you might make some mistake in terms of the computation and knowing some like the knowledge. That's not that important. What I do really care is you really try to drill the computation as detailed as possible. And then you should like think about what is the like the behind and can we generalize some like pieces of the computation in your own way? So with establishing some of the conjecture, and if you are indeed able to prove something, then that's your result. So, and this like the seminar is to just keep your own pace to just study and just keep what you wanna take your own interest. So that's the spirit. So that if you are super busy, so in certain week, so definitely you can skip the like the presentation. That's completely fine. But by just keeping this like the pace of the presentation of some of the detail, you can keep your own interest, and eventually you'll do something. So that's the spirit. So Tate, you can share your screen and yeah, let us start. So you should unmute your mic first.
Hey, hi guys. And I remember at the last seminar, I introduced the stochastic integral such as Ito integral and Stratonovich integral. And I guess you have questions like what's going on and why should I consider this integral? So in this seminar, I want to oh, I introduce a probabilistic approach for PDE and how can we connect probably probabilistic approach and PD is using we call generators, infinitesimal generators. So let's start with simple some a simple Dirichlet problem. You can see here uh, the Laplacian is zero, and the boundary is boundary condition is like this. And we can easily get the solution is a linear function like this. And we can use the maximum principle to show that the solution is unique. Like for example, we set the W. If there are two solutions U1 and U2, then set the W as the difference between them. Then maximum principal said the maximum principal said the maximum and the minimum are on the boundary of the domain. So the the W should be should be zero. So the solution should be unique. But how can we use the probability tools in this problem? Well, let's consider the stochastic process like this. Well, we will talk about this later. So we don't concentrate on what it is. And let's set the let's set the well the time variable. We will call it as hitting time. But I'm not sure we will go details about this. And we each about the time to hit the boundary of the domain. For, but it is a random variable, not the exact a variable, because xt is the random variable, so we cannot say x become zero at exact some time, or we can or one at exact some time. So the time is a random variable in this case. Just to we just to understand you can understand this as a time to hit time hitting boundary. Then let's compute this. Well, for the g is the function at the boundary, like at g is a at 0 and g is b at 1. It is just comes from this here. So the expectation because g has only 2 points, so we can calculate the expectation like this. And the problem is what is this value? And we can easily calculate using the expectation of xt and the expectation of the Brownian motion, and we get xt is expectation of xt is x, and the expectation of xt is expectation of the x at hitting time is the probability of the x is at s is at the point 1. So this we can easily calculate that this problem is x, this probability is x, and this probability is 1 minus x. So the expectation value is exactly the same the unique solution of the Dirichlet problem. So we can more generally we can connect the different PDE and the PDE and probability representation like this. If you have a differential equation and the boundary condition, then we can uh, construct the diffusion process using the operator.
There's a question.
Uh, yeah. Yes. Hajin, please.
Yeah, yeah. I think I missed why the expectation value of WT is 0. So, is that
Okay.
trivial thing, or
Ah,
could you explain to
yes.
me?
Yeah. I didn't say. I didn't say WT is the one Brownian motion, and the
Mm.
definition of the Brownian motion is the expectation of the definition is each distribution is the normal distribution
Oh,
with
okay, I see.
the mean is 0. So the
Mm.
expectation is goes to 0.
Yeah, then I can track your computation. Thank you.
Mhm. So we can define the we can construct the diffusion process that related to the second order operator. We will see later. And here, heating time, where we will not spend much time here, and the boundary condition, and then the solution can be obtained by this equation, this calculation. Also, the heat type PDE can be uh, the PD type has also second order differential operators, and also we can construct a diffusion process from the operator, and the solution of this this type PDE can be obtained from this equation. We will cover later. Maybe 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 not this time. Maybe later. So what is the what is the diffusion process? What is the different process? The diffusion process is defined has the form like this, and we will call this part is drift, and this part to be a martingale part. As I mentioned with at the last seminar, uh, the differential form is actual meaning of the differential form is the integral. So we can if we can represent the diffusion process like integral form like this. Uh, I should that mention that the martingale the martingale is very important in the in the theory and also in the calculation, because it reduces the heavy calculation of the from the very good very good property of it. So define the martingale first. So martingale is defined by these two conditions, and first one is clear, and the second one is little difficult. It seems to be difficult, but it let's So I write the FS is a filtration, but you can completely ignore you can ignore completely just about the filtration. It can be thought as a information. So FS is represent FS represent the uh, whole collection of the information up to the time S. The how can you say the observation value of observations up to the time S. Yes, yes.
Um, what is the meaning of information about filtration?
Uh, it's very
Yeah, I think it is
I, I,
related to my work. So yeah,
okay. So
it's just a question. Yeah.
It's completely analytic concept. So well, the concept of the Gaussian process is the uh is the is not to describe the infinite point of the process, right? Gaussian process, the concept of the Gaussian process uh is the re- description of the finite value of the process. Only we can describe the finite value of the process, not the whole process, not the whole point of the process.
So let me give you some like a comment because this is important like a question. So and of course we need to learn this like the basic setting. I mean the foundational setting of the probability space answers, the stochastic processes definitely, and also the important like the definition of the conditional expectation from the Radon-Nikodym theorem whatsoever later. So but the intuition of the filtration is the following. So we imagine the time evolution of the random variables. So each time there is a random variable that we'd like to do the sampling from its distribution. So we just set up the initial time as 0, and as t goes by, each like the t there's a random variable. So and with each of the random variable we will take the sampling from that distribution. So that as t goes by, we will then make the stochastic path, random path like that. But in order to randomize, so we should really regard, mathematically speaking, each t there's a random variable, right? But what is the definition of a random variable? So we saw that each of the Borel set, so the inverse image should be sit inside of the sigma field. So that's the definition. So the way to create that like a sigma field is, so we will just make the smallest possible sigma field or sigma algebra that makes each of the inverse image of the Borel set becomes the event. So as t goes by, so the intuitions as t goes by, we will take the smallest possible sigma field that from like the 0 to that t. So all those like the collection of the random variable becomes the like the random variables. And in order to do it, we will like the putting additional like the events if this condition is not satisfied. So that this is the like the evolution of the information in a way that as t goes by, then we will just make the each of the functions to be random variables. In order to do it, we will put additional like the elements of the inverse image of the Borel set. Then this is a kind of the expanding like the family towards the ultimate like the sigma algebra, and that's what this natural equation.
Is that the same meaning of filtration?
Yeah, that's the
Or
same meaning of the natural filtration, meaning that for each of the t, then from 0 to t, we will take the smallest sigma field for that fixed like the key to make all those random variables are indeed random variables, not just the ultimate like the largest like the sigma field. So the reason is that if we are doing, for example, the gambling, then we just have the information of the events from like the 0 to t, so that we will not add the addition like the events from the future time. So that we will take the, in that sense, mathematically smallest from 0 to 2 to make all those from the past to the current like the stage, those random variables are in the random variables. But for the future information, we still do not know anything else, so that we will not put any of the additional events for that. That's the meaning. But of course, we need to drill so mathematically what this really description stands for. But this is what it is.
Okay, I see. Thank you.
Yeah, thanks.
Thus, this second condition is the expectation. The expectation of the future value is same as the current value of the process, because we have information up to time s. Second condition is the meaning of the second condition is this. So the very important example of martingale is the Brownian motion. The first condition can you can calculate the absolute value of normal distribution, expectation of the absolute normal distribution. So you can check your own. And second condition can be like this. So we use this and we can split this addition. And because we already we already know the value of the value at the time s, because we have already information of the up to time s. So this value is just bs, as we know. And here we have information up to time s, but the increment of the Brownian motion from time s to t is independent. So it depends on any information. So this is just the expectation of increment, and we know that this increment distributed in normal distribution. So this expectation is 0. So we get the second condition is satisfied in the Brownian motion. So the Brownian motion is the martingale. And the most important fact is the Ito integral is a martingale process. I will not cover how can we obtain this fact. I will use it as a fact. And my last part of this seminar is the infinitesimal generator of the diffusion, which is the bridge of the connection of the connection between the PDE and the diffusion process. The definition of the infinitesimal generator is this, and we can easily understand that is the infinitesimal change of the process. It's like a kind of derivative. So we call this operator A is the infinitesimal generator, and for the division of the phone like this, uh, the infinitesimal generator is given by this. For example, the Brownian motion is here. B is 0, and Brownian motion is B is 0, and this is identity. So here goes 0, and this part is goes to identity. So we get the generator is a half of Laplacian. As we, let me let's go back to here, back to the first page, and here is the Laplacian in one dimension, and we construct the diffusion like this. The x is just a constant, so we can ignore this, and wt was the one-dimensional Brownian motion. So this set this process and this second order differential operator is connected. So we can use this as a tool of the PDE. My former calculation, I will show my former calculation. I concentrated in the Schrödinger equation of the Schrödinger equation and each eigenvalues, and I faced this differential equation, and at the definition of the generator, we define the process first and get the operator first, operator then, but we can do it conversely from the operator. We can construct the correspond diffusion process. For example, if we have a half Laplacian, then set B is 0, and sigma to I, then we get Brownian motion. So similarly from this equation, or let me see, from I get, oh yes, here this operator, and using this relation, I construct B and the sigma. So I constructed the diffusion process like this. So if you have a second order differential operator, not or operator, but most of them, you can construct a diffusion. And then we can use stochastic tools to explore the differential PD problem. Well, this is the end of my presentation. And have any question?
Yeah, so I have a few comments on today's presentation. Yeah, so very well done. Few things which are very important in our aspect. So I will also leave this like the comment on the Discord channel so that they can also look at it later accordingly. So first, so if you go back to the second page of what you prepared, related to the correspondence between, yeah. So sorry, third page. Third page. Yeah, so this part, the correspondence between the Dirichlet problem and the probabilistic representation. So this is very important. And as take prepare in the like the R1 setting. Uh, I highly recommend all of the participants here, if you are if you are concerned the probability theory for your own research eventually, so just replace this L by the 1/2 of Laplacian or just Laplacian, and then try to connect this with the convolution by normal distribution explicit. So that gives you the intuition. Just solve the heat equation, and the unique solution will give this like the stochastic representation. It's just nothing but the reinterpretation of the convolution by the normal distribution density with the initial condition. Once you just compute that out by yourself, then you can exactly see what this is. So, but I'd like to recommend take to do two computations by yourself. So one is, as I pointed out, we'd like to know establish the intuition regarding the correspondence between diffusion process and the diffusion operator. So one is with the standard Brownian motion and the 1/2 of Laplacian. So I think this part you already know how to do it. But another computation I'd like to add is between the so-called Ornstein-Uhlenbeck process. This is another type of the Gaussian process, and connect this to the diffusion. This case diffusion, not only the second order part, there's a first order, the gradient part. And the important like the reason to add this one is there are two reasons. So in general, we are not able to explicitly describe the Markovian processes. That's not possible. But these are exceptions in a way that we can do our computation explicit. That's one reason. And another reason is that Ornstein-Uhlenbeck process. So this is related to the Lich curvature tends to negative infinity, whereas the Brownian motion has is defined on the Euclidean space, so the Lich curvature does a zero, so that it distinguishes from the geometric phenomena from the Lich zero to Lich negative infinity. So that in that sense, Ornstein-Uhlenbeck like process, just adding the gradient like the first order derivative matters, and this can be done by just using the one-dimensional Taylor expansion. So I recommend you to do this computation and share this computation in this seminar. So this will give us the good intuition. And another part that I'd like to put emphasis on what is the genuine importance of the objects. All we actually have is just the generator. So all others correspondence are quite abstract. We are not able to describe at least in the explicit way, but the generator is what we can really genuinely have. So it is important to think of the geometric like the part of the generator. So for example, what is the meaning of so if you go to the martingale part that you define and you give the Brownian motion as an example, if you go that page, yeah, here. So for example, so we can of course check the absolute value of the Brownian motion expectation satisfy the right-hand side. So this is just a purely the computation part. I agree with that, but now we actually define new process, not just the Brownian motion, but the absolute value of the Brownian motion. So this is now new process that we like to call it by the so-called Bessel process. So that as long as we have a reasonable process, then there must be the generator. Then this generator should be described geometrically so once we have the Laplace Bertrami operator on Riemannian manifold, then we prefer to work on the geodesic polar coordinate or the geodesic like the coordinate or exponential like the map should be used for our like the local coordinate, right? Then we can take the radial part with the angular part. So if we throw our angular part away, so that this is the radial part of Laplace-Bernoulli operator given on with the given Riemannian metric, that gives the Bessel process. So the Bessel process, the corresponding generator is just coming from, we have the one half of the Laplace-Bernoulli operator first, using the geodesic polar coordinate, then just throw the angular part away. And then the rest of it just coming from the radial part. So that's the desired like a diffusion operator. That's one intuition. So the generator already contains our geometric feature. So this is the key, the genuinely importance. So as you pointed out, why there's a freedom of the OM action of the Euclidean Brownian motion? Because once we have the generator, if we regard that as one half of the Laplace-Bernoulli operator, then we already know what must be the Riemannian metric. And the Riemannian metric, if we act by the orthonormal, like the group, it will not change anything because this is just a Euclidean action. So that's why even we just multiply by the orthonormal matrix on the Brownian vectors, so still the generator should be the same. So it will produce the same Brownian motion. That's the idea. So that the isometric group will not change anything in terms of the generator. So of course, the proving is slightly different like the issue, but this already gives us the good intuition why it should be just preserve the same type of the processes and so on. And just one like the last part. So if you are ambitious to do this sooner or later, so in terms of the genuine project that you might get involved, I want you to do some heavy computation that does not need to share on the seminar, but it's good to do this computation by yourself and then keep it for a moment. So two parts of the computation. One is do this correspondence with the so-called the Heisenberg group. Then this can be also do everything explicit. But so again, this is related to the Lich curvature tends to negative infinity. So that the reason to do this computation is that so the Euclidean computation is probably just a well-known eventually. But if you just have the intuition on the Euclidean setting, if you transfer a setting to the Heisenberg group, this could be already new. So that I want you to just establish not just satisfying with the Euclidean setting and also Riemannian manifold, but just try to expand the computation over the Heisenberg group. That's one thing. And also we care the discrete setting also as well. So just replace the Laplacian to the so-called Grec Laplacian, and then just do the computation. So these two give you some idea. If you know how to compute the stochastic calculus in the Euclidean setting, then you know how to expand to the non-trivial like the classes. Those are the comments I also want to give. And the Bokuno formula that you know from the geometric analysis is related to the Lich curvature. So once we have a generator, then we will generate the first and the second Kreidt-Champ, and then that already contains the information of the Lich curvature. That's also important, like the part of this like the computation. So the generator contains everything, and stochastic like the process like the part is closely related to the choosing the reasonable stopping time, and the reason that martingale part, so by taking the expectation it just vanish, is the abstraction of the quotient integral formula, first we told, quotient integral theorem. So because the probabilistic like the interpretation is coming from the harmonic function, and the real dimension 2 case harmonic is actually essentially same as a holomorphicity. So that quotient integral theorem is now abstractized into this stochastic way. So this is also related to the complex analysis also as well when we talk about the martingale. But so I also invite some of the participants here to like review the basic like the terms. What is the meaning of the conditional expectation? What is the meaning of the martingale? So in terms of the description, mathematical description, and just go over the concrete example of the normal distribution on R1. This is also good to review all together to foster the necessary conversations. So that's our comment I'd like to put today. So if you have any questions, please let me know. Otherwise, if there are any other comments or other parts of discussions, then I can wait for a moment. If not, then Andy will be the next speaker.
Okay. All right. So let me share my screen. Okay. So in the
first week, I presented on the Schwarz lemma, and I mentioned that in combination with a few other things, the Schwarz lemma can be used to prove an additional result called the Schwarz-Pick lemma, and that's where we're going to end up today. Before we do that, we're going to want to use the metric on the disk, on the complex unit disk, to establish a explicit distance formula. And so we're going to take this metric, we're going to substitute our complex variable z in the radial form, and we're going to get this expression, and we're going to start by calculating a distance formula between the origin and any point z. And so here we can simplify this expression greatly, because for a distance that's between any point z and the origin, our distance is on a radius. So our d theta right here is equal to 0. And so now our distance between any point and the origin just becomes this integral from 0 to the modulus of that point of ds, which is now going to just be 2 dr over 1 minus r squared. The bottom of this, of course, is a difference of squares. And if we do a partial fraction decomposition on this now, we'll get 1 over 1 plus r plus 1 over 1 minus r. And our result that we get of the natural log of 1 plus modulus z over 1 minus modulus z, this is actually really close to our definition of the hyperbolic arctangent. And so we get a distance from 0 to z that is just 2 times the hyperbolic arctangent of the modulus of z. To compute a general distance formula in the disk, we're going to take any 2 points, z1 and z2, and we are going to apply one of our phi automorphisms, specifically phi z2, that we established last week. So this automorphism here is going to send z2 to 0. And so this distance from z1 to z2, we can write this in terms of a distance from 0 to phi z2 of z1, which we're going to get 2 times the arctangent of modulus phi z2 of z1. And so here's the final expression we get for distances in between any 2 points in the disk. So now with that distance formula established, we're ready to talk about the Schwarz-Pick lemma. So this is a result that is going to ultimately tell us that all holomorphic functions on the disk are contractions of the Poincare metric. So our distance rho f of z1, f of z2 is always less than or equal to rho z1, z2. And we also have a differential result as we had in the Schwarz lemma. Here, f modulus f prime of z over 1 minus modulus f of z squared is less than or equal to 1 over 1 minus modulus z squared. And as we had in the Schwarz lemma, we have a result in this case if equality holds at any pair or error, so any 2 points Z1, Z2, or if equality holds for the derivative in 2 for 1 point in the disk, then our holomorphic function f is an automorphism. And note the condition we do not have in Schwarz-Pick, which we did require in the Schwarz lemma. We are no longer requiring that f fixes the origin. All right. So in order to apply the Schwarz lemma to prove Schwarz-Pick, what we're going to need to do with our general holomorphism is we're going to need to use it to construct a holomorphic function that does fix the origin. We are going to define points W1 and W2 as the images of Z1 and Z2 under F. We are going to use, once again, these are our conformal automorphisms that we talked about last time, and we are going to construct a composite holomorphic function that is going to be this psi W1, which sends W1 to the origin, composed with F, composed with the inverse of psi Z1, which sends Z1 to the origin. And then we can calculate then that G applied to the origin, if we work through this composition, produces the origin. So now G is a holomorphic function that fixes the origin, and we can apply the Schwarz lemma. So let zeta be in D. And now the Schwarz lemma says that modulus G of zeta is less than or equal to the modulus of zeta itself. So we specifically let zeta equal psi Z1 of Z2. And we'll get the G of psi Z1 of Z2 is less than modulus of psi Z1 Z2. And the left-hand side of this inequality just works out to psi W1 of W2. And so we get this resulting inequality, which actually gives us that we have f of Z2 minus this f modulus all f of Z2 minus f of Z1 minus 1 over 1, all of this. Well, these are actually almost in the form of our distance formulas that we established before. What we're missing is 2 times arctangent on each side of this inequality star here. But arctangent as a real value function is strictly increasing. So if we apply 2 times arctangent to both sides of this inequality, the inequality is preserved. And now these are exactly our distance formulas between f of Z1 and f of Z2 and Z1 and Z2 in this inequality. That proves the first point. If to show the second one, this derivative inequality, we're going to divide both sides of this right here, our inequality star that we established earlier, by modulus z1 minus z2, and we're going to take the limit as z1 approaches z2. And we'll end up with precisely our derivative inequality. Prove the cases of equality being automorphisms. Let's go ahead and suppose that we have equality with z1 not equal to z2. And then we're going to look at the composite function g again. And there's a point zeta naught equal to psi z1 of z2, which is not equal to 0. So modulus g of zeta naught is equal to modulus zeta naught. Again, by the Schwarz lemma, which we can apply again because g fixes the origin now. G is simply a rotation. In the differential case, we're going to let z naught be a point where equality holds. And then applying the chain rule on g, we get the modulus g prime of 0 is precisely equal to 1. And by the Schwarz lemma, once again, it's an automorphism. So the major takeaways from this lemma, first of all, that holomorphic self-maps of the disk contract the hyperbolic metric on the disk. Equality characterizes automorphisms of the disk, and this identifies the automorphism group of the disk precisely as the orientation preserving isometry group of its hyperbolic metric.
Right. So any comments or questions?
I have a question. I'm very uncomfortable to think of all of these things because I wonder why it must be automorphism. This automorphism should be isometry. I think this step, uh, since this map is isometry, we can think the metric uh, such that this group should be isometry. I, so I wonder this intuition is correct anyway, uh, because we have an automorphism group and if we want to make this automorphism group should be isometry, I think this hyperbolic metric may be unique up to constant. This is my intuition. And in this case, I have a question because this have constant negative curvature. But anyway, how we figure out this fact from this automorphism? I have I am not organized, but I'm very uncomfortable to think all of these things.
Yeah, what do you think of Andy for that? I think this is
I don't know that I can directly connect those two things at the moment. I am familiar with a separate way to use the metric to calculate the curvature of the disk. But as far as directly relating the fact that we get that the automorphism group is the orientation preserving isometry group as directly connected to constant negative curvature, I'm not sure I can comfortably do that.
Honestly speaking, I think this is very good answer because this is very deep and one cannot just take one part of the simple observation. So rather than clarifying Lucas' question, I might write something out after we get all other questions. So any other comments or questions regarding this one? So by the way, so Schwarz-Pick lemma is what I did for my PhD dissertation. So I've been studying this at this point around a decade. So still I don't know many things regarding this one. So it's the first like the entrance for the hyperbolic complex geometry, and there are so many things have been discussed. So from the previous literatures, but still there are so many like mysterious parts of the behind structures in it. So one of my like the work is to establish this in terms of the Brownian motions. So stochastic Schwarz lemma is one of my work when I did my postdoc. So I like that result. So if there are no other questions for a moment, then Andy, can I share my screen to
Yes.
bring more uncomfortable with it? So why this is interesting and to care. So details. So that's 1 second. So any details can be derived from this seminar. I'm very sure as long as you guys are motivated. So there are so key terms here. So one is so-called the isometry, and another term is the automorphism. So let me try to distinguish these two. So before I start, I wanna also give you some just a mindset so that if we have a the so-called the Poincare metric. So this means so G Poincare. So it is important to it is defined in terms of the tensor like this. So it is important to specify this the numerator. If this is 1, the Gaussian curvature is -4. If this is 4, Gaussian curvature is -1. And any literatures do not distinguish these two seriously. The real Riemannian geometry uses probably Gaussian curvature equal to -1, so that this should be 4. If this is like the complex context, one should use this to be 1. The key reason here is that then this exactly coincides with the Carl-Theodori and Kobayashi metric for that generalization. So this numerator is distinguished with that reason. So what is this guy? This guy just means an inner product. Inner product at the tangent space at point Z. At point Z. So that each of the point of the unit disk we assign a separate like the inner products as we prefer to call it by the Riemannian metric. And this is the unique Riemannian metric whose Gaussian curvature is -1, equal to -1. So, but the intuition here important is that so we like to draw the set of the unit disk as the open ball. We feel this is okay. Is it okay with you? So we feel this is okay. So that if we copy this picture like this, so as long as we'd like to study this like the structure of the unit ball. So one application that I'd like to discuss is this structure. So this isomorphism, whatever, indeed whatever. So whatever structure you think of, this is the same. So this is isomorphic in any sense, as long as you want to put any like the word here. So this is same as the collection of one-dimensional distribution. Normal distributions. So I anticipate, so this like the identification will appear during this summer from one of the participants here. So indeed this just means so i.e. so that we have theta consists of mu with sigma. Then we have the corresponding Gaussian density. I might wrong, so it might be like this. Probably there's no pi here, but I do not exactly remember. So either it's 2 sigma pi or sigma square. So just a compare with the known like the literature. And so let me just put everything here. Then what you can compute is you can compute the log of this guy. So in the statistics or the machine learning context, this is usually called by the log likelihood function. And then we take the gradient. In the applied context, this is called by the score vector. And recent like the years, there's a so-called score matching. This is very like the widely used in the machine learning with the art of the performance. So score vector, so that we can create vector by taking the partial derivative with respect to mu. And also with respect to sigma or sigma square, depending on what you care. So we can compute this out. Then what you can also compute, oops, just need to put everything down here. So let me put this in the next page. So this guy, then what you can compute is the following important concept of the Fisher information matrix. Let me call that this by capital I. So capital I might not be good notation. So let me call this by FIM. This is the Riemannian matrix. So if you plug in, I don't want to like make any like the confusion on the notation for a moment, so that each component is denoted by S1 and S2 for a moment. Then this guy for each of the theta. So once we fix the theta, then this brings the 2x2 matrix. Then this would be expectation with respect to p theta of S1 times S1. S1 times S2. So if you are familiar with the majority theory, this is so-called the L2 inner product. So with this like the integrand, so you will get these. So that you can compute this out. As long as you know the explicit form of p of theta, so everything is computable, then you can check. This is same as Poincare metric. I'm telling here, not lie, but if you really check this out, then you might confuse. This form is not exactly the same, but I'm not telling you lie, so that you can really see these are exactly coincide with what Andy was presented today. So that the one important like the observation here I'd like to make is the observation and the details that Andy provided is related to understanding of the certain collections of the probability densities, and this feature can be also extended to many different like the classes. So So, but anyhow, this is what I also want to point it out. Then what is the like the geometry, like the spirit of what the Schwarz-Pick lemma and why do we need to care? Then when it comes to study the structure of the set, then we usually study that by the map. We want to study this by the map. So there are two reasonable choices of the map. So this isometry means preserving each arc length. So you can just think of this as a smooth bijection. So let me call it like this. So preserving each arc length. What do I mean by that? So if I just copy this picture, so what if you check and this like the first like the page of the note today, what he first computed is actually this part. He computed this part. So starting from 0, and he just look at this guy and compute this like the length. So this is the arc length. And from the first page, you can see how this computation works out in a sense that if you have a like the curve, gamma of t. So if you have a curve inside of this, but this can be extended to the any manifold eventually, then what you do is you want to compute the arc length, how this works. Then we need to compute if t is between, say, a to b, then we should take the integral from a to b, and this must be dt. This is very clear. Then each of the infinitesimal vector, we need to measure the magnitude. So this should be computed as we have a gamma prime of t, right? Gamma prime of t, then this is the infinitesimal vector, so that we should plug in this into G, Poincare, at point gamma of t. So if you are not familiar with this notation, then this means gamma prime of t as an inner product at the tangent space whose origin is gamma of t. So what was really happening here is that for each of the point, we take the linearization of the tangent space, and at that tangent space, you take the inner product. Then at that inner product for the infinitesimal vector, you know how to measure the magnitude, take the integral to merge all those like the bodies as one quantity. This is we call the arc length. So hopefully this intuition is okay with you. And as long as we know the explicit form of this G, Riemannian metric, so that's why this matters. So as long as this form, and as long as we know all those like the curves explicit, then we might be able to compute this integral. What Andy did today from using the Möbius transform is that if we just convert by using from here to here like this, by using the certain form of in the Schwarz-Pick lemma, the lengths are preserved. So one concept is we want to talk about the preserving the arc length by the bijection. So then we will call it by the isometry. This is the Riemannian geometric isomorphism. So that geometric quantities that we'd like to preserve, then the first like the quantity we'd like to preserve is if we have a bijection, then we can transfer one curve to the another curve. Then if those like the arc lengths these quantities are the same, then we will say, well, this is a reasonable method that we call by the isometry. Is that okay with you? So for example, if you think about a sphere, for example, the sphere S2, then you know how to think of. So you draw R3 as an ambient space, and then you draw this guy, right? This is the way to think. And for example, if you want to measure the arc length between this point and this point, and let's just say this is the curve that we'd like to compute the arc length, for example, then how do we preserve this like a quantity? Just a rotate, right? Just a rotate, and you will see then if you just copy the same picture like this, then what we can do is, well, just rotate this like the sphere. So then we will get, so just put like a put this like the point to the North Pole and there's a corresponding point, then as long as we are able to compute this out in the reasonable way, then we might be able to compute this out, because as long as we have an isometric, then you can actually see what this isometric should be. The isometric should be just rotating the sphere. And this is now described in terms of the orthogonal matrix. By multiplying the orthogonal matrix on R3, sit inside of this S2, then you can see it just rotate. So the arc length should be preserved, so that you might have some good intuition about it. Is that kind of okay with you, what I'm talking about? Intuitive. Of course, we need to prove it, but this works. So, but the behind like the structure is more clear in a way that if I just look at the plane containing these 2 points, for example, then what should the rho is like this. So you have a sort of R2, then there are 2 points, and it's connected by the certain like the arc like this. Then this might be described in terms of the cosine t plus I sine t, like this. Does that make sense? So this is the picture. So that what was really happening here is if I call this point by P, and if I have the tangent vector V at this tangent space. So by using Riemannian geometry, so this could be also one of your presentation that I expect that you should compute geodesic by yourself, so that the geodesic starting from P in the direction of V, this is described as a cosine T times P plus sine T times V. You will get this, as long as this V has a unit length. So that if you plug in zero, you see, you will get V. And in this way, you can see that as long as this T goes to 2 pi, you will rotate exactly so-called a great circle, like this. And this is the intuition that we are talking about the isometry. The funny part is when you look at the hyperbolic space. So I invite you to look at the hyperbolic like the models. I do not know. I am able to find it. So from the Wikipedia page, you can also find the hyperbolic like the model spaces. So there are at least 5 models. But if you now replace this guy by this one, because you know x squared plus y squared plus z squared is 1 for S2. So one of the like the hyperboloid like the model of the hyperbolic space, then you can take this weird model, x squared, y squared, instead of a z squared with adding them, take the subtraction, this becomes -1. This is one model of the hyperbolic space. This is called so-called, I don't know what's the name, pseudosphere. So again, this is same as this, whatever sense you consider. Then if you describe the geodesic, it changes as cosine h tv times p plus sine h t times b. Can you see some like a relation here? This is really the substitution from the ordinary sine cosine to the hyperbolic sine hyperbolic cosine. And if you replace that, then it satisfies the pseudosphere relation. So what I want to point it out here is that now you know how to describe the geodesic. Of course, I leave any of you to do this in this seminar. Is that okay with you? I just take this as a fact with my own intuition, so that you are able to, I hope you are able to verify yourself during this seminar. But now, as long as you know the geodesic in this way explicit, then now what you can expect is that, well, then at each of the point, then we are able to compute this out. Right? Again, one-dimensional calculus. So this is what Andy computed as a so-called rho of Z1 and Z2. Of course, this identification should be done explicit. It turns out that this answer is very weird. So what Andy said is was it like a hyperbolic tangent or hyperbolic arctangent? I don't remember. Sorry.
It was the arctangent.
Yeah, arctangent. Thanks. So what he said is, we will get this. Isn't it look weird? Because now we start from this guy, and take the derivative with respect to t, pulling that into the Poincare metric, and take the integral. Then we know how to compute this out explicitly. And it turns out that that form that Andy presented today is the answer of such a like the form is coming from like this. So that the only such a case is we need to look at such form of the function. Such form, sorry, this is not correct. So how about this one, right? So this is the form of the Möbius transform. It becomes the isometric. The funny part of today's like the presentation is first, so we indeed know how to compute the arc length explicit. That's the first like the non-trivial part. If you really think about the what was really happening in terms of the computation of the calculus, another part is this guy is defined as f and f inverse are holomorphic. This is the order we require for this definition. What is the meaning of the holomorphic? Holomorphic just means complex differentiable. Of course, there are so many equivalent descriptions, but this is very intuitive one in a way that so that we just need to define this concept. That's it. So if we have this P, then as C goes to P, we have this. And we just require this exists for each P. That's it. This is the definition of a complex differentiable, right? And we just require f inverse exists, meaning that this function is bijection, one-to-one correspondence, and we also require f inverse is holomorphic. What is the surprising part? So first, these two are the same. When it comes to require the automorphism of the unit disk, this is exactly coincide with the isometric. We are not just saying there's a relation. We are saying they are exactly the same. That's one surprising part. And another surprising part is this is based on what Loki commented today. So from complex analysis, you can learn that this is very weird. So if you require f is holomorphic plus non-zero derivative, okay? Let's require a further condition. So differentiability does not require derivative to be non-zero, right? So let's just assume further condition that if this is non-zero, then f is so-called the conformer. Conformer means preserving the angles. This is very weird. So what I mean is the following. So now this is my last like a picture that I'd like to draw. So we have complex plane. And we have a certain map here, so that you draw two like the curves like this. Okay, two curves, curve gamma 1, gamma 2. Then let's just move by using this function. Then you get, for example, this gamma 1 might be like here, f of gamma 1, but they share the same common point here. Then gamma 2 might be here, f of gamma 2. That's what I mean, right? So let's just assume this is holomorphic. Plus, so f prime at this like the point is non-zero. Meaning of the preserving the angle is that now you take the infinitesimal curve. This guy, right? You're able to do this so that you are able to measure this angle. And then now you move this another like the curve. Then you can also take this infinitesimal part. I'm very bad at drawing. And also this part. Then also you are able to measure this angle. So let me call by this theta 1, theta 2. So what this conformality says is that they are the same for any f such that f prime at that point is non-zero. Of course, f is holomorphic. So this is what we know from complex analysis. Of course, this is very like a also in foundational fact by using the Cauchy-Riemann equation why this holds. But so let's just even take this as a fact. So if you now compare the meaning of the isometry and the meaning of the conformer, they are different. So isometry means each of the curve, it preserves the arc length. Conformality means each of the angle that should be preserved. So you see, geometric features are different. But in the case of the hyperbolic space, it turns out that they are the same. As long as it preserves the arc length, it must preserve the angle. In general, the conformality is slightly weaker than the isometry. Isometry actually implies a conformality, in fact. But conformality, as long as you just preserve the angle, we do not require it preserves the arc length. Then it turns out that it preserves the arc length also as well by using this non-trivial computation, and the Schwarz-Pick lemma play a role to compute the geodesic distance. And again, this also is related to understand the geometric structure of the normal distribution. And one of the foundation fact of the statistics and information geometry is called the Cramer-Rao inequality. So if you look at Cramer-Rao inequality, at some point, you can see this is related to Schwarz-Pick lemma. So that we established a certain type of the inequality related to the unbiased estimator and the inverse of the Fisher information matrix. But you can actually see there's a very the deep connection by just understanding the Schwarz-Pick lemma. So you see, so it's not trivial. So as if we go back to Loki's question, why conformality makes the isometry in this specific setting? Of course, we know how to prove it. Does not mean that we might not have a very good the interpretation about it. So yeah, still I do not know how to think of. So it's all related because it also is equivalent. Say Gaussian curvature is constant everywhere, and there are so many equivalent the conditions, but yeah, not clear. And also, by the way, so in the generalization of the Kobayashi and the characteristic metric from this observation, those types of the geodesics are very worthwhile to explore and further research. Those geodesics are extremely hard to study in general. So this is very a good the direction of the studying hyperbolic geometry also as well. Yeah, I will also leave this the note so on the Discord channel and also here. So any other comments or questions? I just try to address why this Schwarz-Pick lemma is so interesting. And if one goes to the higher dimensional complex the spaces, then even for understanding of them are extremely interesting. And for the higher dimensional normal distributions, this is also closely related that also possess the hyperbolic structure also as well. Is that clear what I want to address here? Why this is non-trivial? And again, I invite any of you to just compute this or out by yourself by using the elementary calculus, and then just check with all others here. So this is important as well. So if there are no other comments, then we will move on to the Landon's presentation today.
I have documents.
Sure.
Well, it's very impressive the whole pyramid, decidedly the orient preserving isometry, but I think the orient preserving is also important because
That's true.
Because such intuition, we can imagine the origin inversion, then it could be a automorphism.
Right.
Because it's isometry,
yeah.
But it's not holomorphic. So
right. Exactly. Right. Yeah, I agree. So when it comes to think about the reflection map, for example, yeah, so it's not clear for me. Yeah. Thanks for that comment also as well. These are what you guys should think of and try to develop anything further. So if there are no other comments, then yeah, Lander, now it's your turn.
Yep. Go ahead and share. Okay. Okay. Okay, so for today, what I really wanted to cover are the topics of ramification points, branch points, and covering maps. I also wanted to prove some things. I think I got a bit over my head when I wanted to do that live. But at least at a high level, I want to bring up some of the things that I had proved over the week. And then maybe another time we can get into the actual proofs themselves. So that's what I have, and the motivation for why I care about these things is eventually there's this concept of degree that has both a meaning in arithmetic dynamics, so in number theory, but also has a meaning here in geometry. And it turns out that there's going to be some connection between degree and what's called height, a very important concept in arithmetic dynamics. So to understand degree, I first need to understand the topics above. I don't think I'm going to get to degree quite yet today, but there's going to be enough information where it should be easier to get to it next time I talk. So the context I'm starting with, and I don't know how much knowledge everyone has of like manifolds, mapping between manifolds. So when I took Dr. Cho's class. I had never seen it before. So for me, it was new then. It still feels new. So there might be some things that I talk about that are very basic, but just bear with me while I go through that. But for the context today, we're going to be mapping between two different compact connected Riemann surfaces, and we're going to be looking at non-constant holomorphic functions. So as Dr. Cho just said, holomorphic function means we can define the concept of a derivative, and even more fundamentally, of course, as part of that, a limit in the complex plane. And then a non-constant is what gives us some interesting behavior. And so it turns out that under these assumptions, in the open mapping theorem says that, well, this mapping is going to be open, one, and it's going to be surjective, two. And so that surjective part carries a lot of weight as well because it kind of means that you're going to be mapping one space over an entire other space. And so you have this concept of coverings coming into play. And so I just want to show a few pictures of what that kind of looks like, sort of like what these ramification points and branch points are, before I like get into a more formal definition. So last time Dr. Cho actually showed a similar example, or probably the same exact example. But this is an example where I'm going to map a torus, a complex torus, onto a CP1, which is essentially the same as a sphere, right? So if you start with a torus and you kind of split it in half down the middle, just like ignore the points for now, I guess. But you can kind of fold it onto itself. So the orange part here maps onto the green part. And then you kind of get this like half piece of the torus, but then you have the endpoints closed off, and then you can kind of squish it down into a sphere, right? And so that is the idea of mapping between the two. When you do that, you tend to double map essentially the torus onto the sphere. And that's what I'm trying to represent with these two layers kind of like going on top of each other, is that it's covering it a couple of times. And then, of course, now the thing is that not all points are going to have a double mapping, right? And these are the special points called ramification points. And so I've shown what they are here in purple. So it turns out this particular mapping has four ramification points. And so I track them through the mapping here. So you can see 1, 2, 3, 4 across the middle. Here they are once we fold the torus in half. And then once we kind of put it into we smush it into a sphere. Here are the four ramification points. So basically every point except for these four get mapped to at least in this picture twice, right? So I haven't proven here that there's a essentially gonna be a degree two here, but what I'm just kind of illustrating that here. Now there's a weird interpretation with these ramification points as to what's actually happening here. It I'm not very comfortable with it. I tried to represent it in some other pictures. Um, but basically all it really means is that under the mapping, these points are only going to be mapped to one time, whereas everything else around it is mapped to more than one time. That's what these that's what happens here with these ramification points under mapping. And what other than ramification points would you have, right? Well, we also have these points that have this nice symmetry about your line over which you're kind of like folding the torus. And so these are going to map onto the same point over here. And so this yellow point is referred to as a branch point or a branch value. And basically the one way to think about that is the function that we're using to map is no longer locally invertible, meaning that is if you look kind of like in the backwards direction, right, this yellow point, this branch value is mapping to multiple or is mapped to from multiple points over here, right? And that's the underlying kind of mechanism over which you're covering the space two times is you're getting 2 points and you're mapping 2 points to 1 point everywhere here in this picture. Okay. So I think I covered at least the high level of each of these topics. I probably, yeah, just given the pace I'm going, there's no way I'm gonna have enough time to do like proofs, but I just wanted to show you this. So let's say like another example is you can map, and I'll show these examples again later. So I'm just kind of like flashing the pictures right now. But another example is when you map the CP1 onto CP1. You kind of start over here. You can think of, okay, I'm going to take points over here on this sphere, and then they're going to kind of map onto themselves over here on these. And this is just showing like one open set, right, and how it maps. And then you have this point, the origin, which isn't going to be mapped to twice, right? It's only going to be mapped to once, right? Um, right. Okay, cool. Um, so like what's a covering map? So I just have the formal definition here. There's so many definitions. Like if I were to go through all of them, it would take a really long time. But this is one that I don't think takes a whole lot of background, other than like topology. So a topological covering map is just a continuous surjective map between the spaces, where if every point has an open neighborhood such that the inverse mapping or the inverse, the pullback here is a disjoint union of open sets in the domain. Basically, if you look at it's a covering map, if you look at the open sets here, right, and then under this inverse image of P, you can go back and find multiple homeomorphic images or some multiple homeomorphic sets that are mapped to it under P that are disjoint, right? And that's kind of that's like a key feature is this disjoint piece, right? And that's why what we think about the map being kind of covered over, or the map covering over the target space multiple times, is you have these like homeomorphic images kind of like stacking on top of each other. One analogy I've seen is like this is like stacking these three like pancakes on top of each other from the domain space to the target space. And so that's like a key feature of a covering map. Yeah, again, there's a ton to go into. There's okay, well, if you have a general manifold, how do you even talk about, a point in space? How are you even going to dream of doing calculus on it and all of this? So you have to start with the concept of an atlas, and go into that. Where that's really just saying, hey, I'm going to take every single open set on my general manifold, here. And then in the case of a complex manifold, and a Riemann surface, I just want to go ahead and map that to C, map that to some open set in C, that's homeomorphic to that original open set. So if let's say on the left-hand side here, I have this like double torus looking thing, and then on the right-hand side, I have this like other manifold, right? In general, those don't have coordinates, right? So I have to build out these kind of ordered pairs um, of phi and an open set, let's say U. And I have to do that for every single open set. And then in the case of Riemann surfaces, you actually need to build out what's called a maximal atlas. And then once you have a maximal atlas, you can start simplifying the local math really, really nicely. So you're looking at basic polynomial equations, instead of full power series everywhere. Um, that's like one motivation as to why we get into this like level of detail, is it then allows us to really simplify things later on. So a lot of what I proved this week, like in my own time, was understanding, I guess, the mechanics behind why you can write this simplified versions of these maps at certain points. And that helps with understanding what a ramification point is, what a branch value is, and so on. And so just to show you the breakdown of concepts, right? So you can start with this atlas. I'll just go through all three properties. One is you have to have a collection of all of these what are called coordinate charts, so that you cover the entire space. Um, and then it's an open cover. The next is you're going to have homeomorphism between these sets and some in general some field, but in this case it's going to be just C. And then the next case is we're going to have something called transition regularity, which is basically, hey, wherever the maps overlap, um, we have to have a nice continuous way of translating from one map to another. And so the composition of these maps have to behave nicely. When you're going from one to the other. So let's say you're here, right, on this manifold, and you have a different map, let's say over here. Let's call this like row. Okay. And so at their overlap, let's say you start out with your description in terms of row, and you want to now describe it in terms of phi. You have a continuous way to map between the two at this overlap, right? All of that's really important for the proofs. Again, the one proof would I would not have enough time to do. So, but those are the types of details that end up mattering. So you have an atlas above. You have a maximal atlas, which just means that pretty much every possible, you can start with an atlas, right? And then you think about every translation of every single mapping in that atlas. You think about every even not translation, but even like a change of variable in there. And then basically say, okay, any single one of these Any single one of these translations or change of variable are also going to be found in the atlas too. And so Riemann surfaces have at least the ones, at least as far as I've studied, assume a maximal atlas. So you're always able to kind of translate your coordinates, change your variables so that the algebra locally looks really nice, basically. And so in the case of Riemann surface, you're going to have a nice biholomorphicity of the transition maps. So the transition maps are holomorphic, their inverses are holomorphic, right, as well. Okay. So that's just the high level of everything there. So again, the context is we have two surfaces. They're going to be compact Riemann surfaces. They're going to be connected as well. And then we're going to look at functions between them that are non-constant holomorphic functions. All right. So the first kind of big piece of this is we often talk about this function because it's the direct mapping between the two. But in general, what we're really talking about, and if I were to erase a few things to simplify this picture, what we're really talking about is the inverse mapping of this function, right? And then on top of that, we're going to compose f. And then on top of that, we're going to compose psi. And that gives us a way to go to basically create a map from C to C, essentially, and do the math of C to C to represent doing the math on these between these manifolds, right? And so it's this function that we're really writing the let's say like the power series for, or simplifying it for, as opposed to necessarily this one, right? So that's the first thing that I really had to learn. In fact, I wrote some of these things here with F instead of F tilde. I think it might be a shorthand that other people use too, but maybe not. So the first thing I learned is that, and this I actually learned in Dr. Cho's class, is these mappings can take on a really nice form of just mapping to z to some power e, right? And this is it turns out this form is really descriptive of what's going to happen with these ramification points, the branch values, and then also the covering maps. This power of e holds like all of that information essentially. And so this E is called a ramification index, right? So it's like, okay, I want to take a point here, just pick any point, right? And I want to represent that point as a Taylor series, right? Okay, so you can do that, and then you can change the coordinate. You can translate your maps around to center everything at 0, and then you can also change your variable so that you just end up with z to a power of e at that point, right? And again, you can do all of that because in a Riemann surface, you're assuming all of those transformations are within your atlas, right? So the first thing I had to do to really convince myself that that was possible was prove that is indeed something that can happen. But this feature, this exponent here, is called a ramification index. Any point which has a ramification index greater than 1 is called a ramification point. And lastly, this is the big thing, is regardless of what chart you use, if you can get it in this form, or if you can get it in a form close enough to that, this E value is always going to be the same, right? So it's independent of any charts you pick, any translations, you should always get the same E value, the same Z to the E value out in front. Now you might have something like Z to the E times G of Z when you're representing, let's say, F tilde Z. Right, but and then this ends up being something like a non-zero constant, let's say A0 plus A1 Z, right? This can be written like that, where A0 does not equal to 0. But even in this case, this E will always be the same, right? So yeah. So there's a big long proof for that. It gets into a lot of things. Here's a couple of pieces of it. Open mapping theorem, of course, is going to be important. Defining the uniqueness of E is going to be important. Knowing the definition of a logarithm is one way to go about it. There's 5 ways to define that, by the way, in complex analysis that I found. Knowing about the existence of a local analytic root is really important. That means, okay, I can take the ETH root of these really complicated power series or these power series, right? And then I can represent that as a holomorphic function. And then Z times that function can then be a change of variable where you take that to the ETH power, right? Or you take that product and that becomes a holomorphic function. Under change of variable, you can replace that by one letter. So there's quite a bit there. Um, right. But the big thing is, okay, once you understand that near these ramifications, once you understand that these points locally can be written as Z to some power, right? Then you can start to analyze, well, how do these maps break essentially? Where is it the case that they fail to be locally invertible, right? Um, and so that is actually not at branch values, by the way. It is actually at ramification points, at least one way to look at it. Um, so a bit of a correction there. But basically what you'll find is in analyzing this, you can find multiple roots of Z to the E, right? This is like the essence of it, right? So Z to the E is generally going to have E roots. And what you'll find is on this side of things, if you're mapping to a point, let's say like under this map, it's Z squared right here. You're going to find 2 roots over here that you're going to map to this Z squared. And so in this space, on an open set containing Z, right, you fail to be able to invert F. Well, you failed to be able to invert the mapping from X to Y at that specific point. Right. So if it's okay, I just want to end on the examples here. So I'll get rid of this. Right. So there's 2 examples I wanted to look at to understand these concepts a bit better. And that's mapping from CP1 to CP1 under this mapping, f of z equals z squared. And then the second is mapping from the torus to CP1 under what's called a Weierstrass, I guess, P function. I didn't have it explicitly written out here. Probably in a future seminar, maybe next week, I'll write it out and we can go through some calculations with it. But it's really the properties that we care about when we're analyzing the branch points, the branch values. And so where does this fail to be invertible? So let's start with the map here, right? And I showed this map earlier. So what I want to do is flip it kind of upside down, flip this CP1 upside down, look at it face on, right? And so I want to split split, if I'm looking at the South Pole kind of like directly on, and I take half of the space from 0 to pi, the other half of the space, let's say I'm like using like just a ad hoc local polar coordinates. So and then from pi to 2 pi, I have this other half of the space, right? So this is in the domain, and I'm going to take it and I'm going to map it under z squared, right? And what's going to happen is 2 points here are going to map to a single point over here. And that's going to happen at every single point about the South Pole, except for the South Pole itself. So the South Pole here is going to have exactly z squared. Sorry. F of z here is equal to z squared right at the South Pole, right? Now, all of these other terms are going to be z to the 1, right, under the mapping, right? F of z is going to be z to the 1, z to the 1. But here, right, we're just going to get a single point mapping to the South Pole. Every other point is going to map 2 times over. And so I know the answer here is 2 because z squared, right, is 2, and then it's going to have 2 roots, and each of those 2 roots are going to map to a single point. All right, so basically, if you take any point w, or if you take any point of w over here, let's say, we're going to have the square root of w and the negative square root of w mapping to it. And then we have that failure of local invertibility because we have 2 different points mapping to a single point. In the case of the Weierstrass P function, right, you're going to have this torus mapping to a sphere by overlapping onto itself about the central axis, giving us a double covering, and then we can kind of squish that into a sphere. And then you can use the properties of this P function, the fact that it's periodic, the fact that it's even, to essentially to discuss what the ramification points are going to be. So don't have a lot of time to do that today. But yeah, perhaps that's where we start next time. Yeah. Okay, sorry, didn't leave a whole lot of time.
Yeah, it is indeed awesome to see all those like the pictures video. So yeah, it looks like some like the face someone. So yeah.
Yeah, right.
So
Yeah.
any other comments or questions?
The uh, at the what is the thing? P function is not a covering map, right? The, and yeah, it's example 2 on the example 2. This just P function is not covering map.
Oh, on the I think so. This should be on.
It's a branch covering, not just covering.
Oh, is that what you mean? Okay.
And
Yeah.
so
So it's not a covering map, meaning that it doesn't satisfy the definition of covering map that we showed earlier. Is that what you mean?
yeah, yes,
Yeah.
actually I want to understand. I want to understand what you want to say. But so
Yeah.
and so the you is there no covering map from CP1 to CP1?
Yeah. So I don't know about covering map, but there's a branch covering, and that's what I meant to say. Yeah. So there's the f of z equals z squared, is the one we're using to map from CP1 to CP1. Um, and it is going to have the branch points at like 0 and infinity essentially. Yeah. Is that what your question was for CP1 to CP1?
Oh, I understand this in this picture that
Yeah.
the South Pole is the branch point, but uh, is it it can be generalized. I mean, the ramification for every ramification map, is there a uh, does a branch point exist always?
So yeah, so the open mapping theorem is the best I got to answer that. All I know is that in the case of, sorry, I lost my document, but in the case of a non-constant holomorphic function between two connected compact Riemann surfaces, right? Then you'll get a branch covering map. Yeah, that's the best. Sorry, I opened the wrong document again. So like back to the beginning here. Yeah, that's the best I got under like being able to guarantee that. Um, yeah, the open mapping theorem. Yeah. Is that, I don't know if that answers your question though. Yeah, sorry.
Yeah, let me try to address what Landon is trying to aiming for doing this. So
Yeah.
it might surpass the time a bit, but still could be good to just mention. So please allow me to take one additional 5 to 10 minutes, so that this might also motivate our other participants to see why we do care these things. So first, like the one of the prejudice I think to say is, so when it comes to talk about the number theory, and for example, algebraic geometry, so he might feel, oh, those are horrible topics. He might think something like that. So whereas when it comes to talk about the manifold theory or differential geometry, you might feel, oh, kind of okay. So So I first want to point it out, this is sort of the big prejudice even in the mathematical community for the advanced level graduates, in a sense that, so when it comes to talk about the manifold theory, you can do the calculus. It does means that you are able to take the derivative, right? You're able to take the derivative. You are able to take the second order derivative, and then you can take the Laplacian and just talking about what is the implication of the first order derivative, second order derivative, and just the curvature, fourth order derivative, and so on, right? So that here you should like recognize, so we don't have equation. This is key fact. So why do we take the derivatives and or higher order derivatives? Because we do not know the equality, or we can control the inequality. That's what's really happening. Whereas, so this word is the word of the equation. You can really insist to talk about the equality. This is a key spirit. So please just compare how this could be powerful when it comes. So for example, quadratic equation, you know how to handle, right? Because it is equal, you know how comfortable with the talk about the equality, whereas differential geometry loses the equality in general, and the corresponding to the abstraction just will give us the word of the algebra, right? Then the geometric, like the understanding, is either the algebraic geometry or arithmetic geometry that we prefer to call by number theory in general, but those geometric, just understanding of that does nothing but the equation or the equality. Then in order to talk about the equality, we need to talk about the group, that the identity elements gives the, like, how do we revert to the identity elements with the equality, right? So it's just talking about the equality. Even in the applied context, just think of, as long as you already know certain relation given by the equality rather than the inequality, how this could be super powerful. So that this is the one like the key theme I wanna think of, that the algebra is not the distinct word from the like the calculus word, but when it comes to combine with the equality, this could be very powerful. So the way to create, so the number arithmetic geometry or algebraic geometry is for creating the equality in a nice way. So for I'd like to just address why do we like to bring this into this like the seminar in the following way, so that we love at least at the seminar we love S2, we love torus. So again, we are not using the power of the equality that much, even though we know how to define them, x squared plus y squared plus z squared equal 1. Torus, yeah, we know what that is, but actually you don't really give a shit in terms of the algebraic relation here. But when it comes to replace this by CP1, so assuming also, so some of you might also review, even though this was already mentioned somewhere, but so as some of you motivates to look at this like the correspondence, I highly recommend you to try to drill as quality as possible. And this can be also written as the elliptic curve. The key point is these are described now in terms of equality. So that the torus, we have just a vague picture so that we can just rotate, even though this gives us a good intuition, that's for sure. But now what? We have this equation. We now have the equation. This is a key point, but the equation here was defined over C. So that this was considered over C before, but now as long as we have an equation, what can we do? So we just need to keep the equation and just change the data of the data type of this x and y. Just why don't we just care this to be defined over ratio? Right? Because now already we possess the equality already. And what if we just change the field to be such as, so field containing not just the cube, but also square root of 2, for example, that we prefer to call it by the number field, denoted by k in general, right? So that, because why we can do this? Because as long as we already possess the equation, right, then we can do everything. So the desire is, so now let's start from the torus, rotating 180 degree, as Landon did very well with the very picture. So this is just a picture. But now when it comes to convert the data to the equality word, then now we have this. Then, so as long as we have the xy pair satisfying this elliptical equation, then we just map by x. But the analytic description of this guy is coming from this, just x is actually p. I'm very bad at notating the bias rate p function, so let me try to resemble as much as like the Wikipedia page. And this like the y is coming from p prime. So that this is a very specific like the power series defined on the torus, which is double periodic. So what like the Brandon did is we just take this projection that called by the p here. So that there's an analytic description to see how this algebraic description was coming from. And once we convert it to the algebraic word, then we can just play with this, the power of the algebra. Because we have equality, the algorithm can be like reduced very like efficient way. So even in the differential geometry world, I want you guys to think of, so how important to find some like the certain types of the equality, and the canonical tool is, so the algebraic geometry, here algebra I also meant arithmetic part also as well, is the philosophically speaking, so how to find a reasonable equation. So again, I just wanted to compare. So if you have a torus, what's the definition of torus? Well, so this is S1 cross S1, no equation. But when it comes to convert to the equation, even though it looks a little bit like the ugly for the first place, but it's a very, very beautiful equation. So when it comes to have the equation, you can just play this, just keep this equation, then you can play everything. So this is a way to do it. So if you have a certain space, such as like a CP1 or like a torus, then you just need to find to embed to the projective space. That algebraic word or algebraic geometry, this is usually called by the Kodaira embedding. So all we need to find is such an embedding. This is the ultimate desire. So then you need to think of why this make all those like the magic miracle in this like the framework. So as long as you find the embedding to the higher dimensional projective space, then you will get the equation. Then the reality of this guy, so it does not depends on the field, by the way. It can be the number field, it can be the Q, it can be C, whatever you care. So this is in fact coming from so-called the zeros cohomology with the so-called divisor or the invertible shift or the line bundle whatsoever. And this becomes the vector space so that you can projectivize. Same for here. So that's why we just we can say, so find the equation just means find a reasonable, either you can call by the either Cartier divisor, equivalently speaking, invertible shift, or a line bundle. So the key reason to reduce to find those objects is we are aiming for find the algebraic relation in terms of this embedding. Once we find the embedding, we are done. Then we know how to do it. So then this data is coming from these data. So that what Landon should like to study through this like the seminar is to understand this framework. So for a moment, we are just talking about the reasonable map of the map from between P1 and P1. And those languages should be translated in terms of either the divisor, invertible shift, or the line bundle and the shift cohomology. So that I will share this like the note right after this like the seminar altogether. But so this for a moment, this seminar will be split into 3 basic themes for all of the participants to study the language. 1, Riemannian geometry. So for a moment, I just split the separate the topics during this summer to see how those topics are related. And once we click each of the motivation, then we need to also work on the digesting the language also. So this is also very important pieces in coming fall, right? So that first part is we should learn Riemannian geometry. When you try to do the calculus computation, you should have the proper way to interpret, so that when you finish your computation with the single variable or the multi variables, then you should think of it as, well, this is coming from the chart as Landon today explained, but not just the abstraction or the conceptual like the explanation. You should know how to drill in terms of your computation. So the Riemannian geometry is first like the language that we need to study together. And now you see, when it comes to talk about the equality, you should learn what? Shift cohomology, line bundle, divisor, invertible shift, those kind of things. That's what we needed to learn in coming fall. But I don't assume we have some of you might not have a proper background on Riemann surface theory. So that was already posted as like a midterm and the final of my previous spring semester course. So it's also good to review all together as Landon tried to review together. So if you have a motivation to learn Riemann surface theory to study algebraic work, so I also invite you to do it, because I heavily like to care even the stochastic context with this equation. So this is also very important. So Riemannian geometry, I'd like to say Riemann surface theory or algebraic geometry, aiming for the shift cohomology to understand this Godara embedding. This is another part. And the rest of the part is related to the probability theory, as Tate is now talking about. So that there are 3 themes of the language, like the description that we all should learn together in coming fall. Is that kind of make sense? But I'm not just talking about, for example, just once we, for example, address the definition of the covering map, but we will not assume from that point we know everything. We will not assume like that. So even we have some certain overlap of the reviewing the concepts all together, that's completely fine. But the key point is you should know how to reduce to the calculus computation. And in that sense, I just want to drill elementary examples as much as possible so that you will get the sense of what was really going on. So that after incoming fall, so I assume you might have certain like the familiarity of the Riemannian geometry language, complex analysis of Riemann surface like the language, and also probability language. And if you take my course in coming fall, then I will also do this work in the graduate like the level of the probability theory also as well. So that's I think I need to talk about. And also it's good to invite any other like the participants to work with Landon regarding understanding the Riemann surface theory and also algebraic geometry together outside of this like the seminar, because we are already connected by the Discord channel so that you guys can also discuss. But do not rush. So does that mean that after this, the incoming fall, you understand everything? I don't assume that. So just go over each of the computations, just one by one, little by little. Just that's all we require. So yeah, it's just out of the time already. But any other comments or questions? And one advertisement for next time. So I'd like to also try to present what he want to study over S2 and the torus. So it is about the PD theory basically, but this also plays a significant role of the Riemannian geometry, algebraic geometry, even number theory, and also probability theory. So we don't expect to know everything for the first place, but still let us try to give a shot. And also I will ask Hajin to give a presentation at some point, but also we'll see them also together. So yeah, and thank you very much for today's also contributions from the two presenters, and we will continue next.